Okay, so the warm-up problem, number one, find the angle of refractance or angle of refracting if a ray of light goes from air to water with an instant of 15 degrees. So here's the water, and then we have air. It goes from air into water with an angle of 15. So that means it's set up like that. The light ray is going into a more dense material, so it's going to slow down a smaller speed, so it's going to get a smaller angle. And we're going to try to find that angle right there. The equation is Snell's law. And we put in our numbers. For air or vacuum, we can just put in 1. It doesn't really matter, this 0.00029, that doesn't change things too much. We can just put in 1 for the index of refraction for the air. Sine of the 15 degrees. N2 is for water, that's going to be 1.33. And then our unknown stays as theta 2. So I'm going to divide the sine of 15 by 1.33. And I get 0.194. Now that is equal to the sine of theta. I want just plain old theta, so I have to take the inverse sine of 0.194. And I get 11.2. Number 2, if a wave enters a material and slows down, will it bend towards the normal or away from the normal? If it slows down, that means that it has a smaller speed. And so that means that it's going to be a smaller angle in the second material. Getting a smaller angle means bending towards the normal. So the word association is a smaller speed, smaller angle. I like that way rather than saying slow down or speed up or that kind of a thing. Okay, last class. In day 123, we were supposed to have done a lab with lenses, and today's purpose, we're going to have a combination of refracting and reflecting in the same situation to produce some kind of effect. And we use this in telephone calls with our fiber optic system and TV crime shows when you see somebody in the interrogation room with a two-way mirror. That is using both refracting and reflecting. How do two-way mirrors work? Oh, I'm sorry, number 1. Usually whenever a wave hits a transparent boundary, you will see both reflection and refraction. Some of the ray bounces off the boundary, some continues into the boundary. And actually, you will even get some absorption, where the atoms absorb some of the energy and the light ray gets more dim. Okay, one of these actions will not be seen when the wave hits an opaque boundary. Which one? Opaque means you cannot see through it, like a brick wall, and so there's no refraction. You have absorption, the brick wall is going to get a little bit warmer, and you're going to get reflection. Light's going to bounce off the wall, hit your eyeball, you're going to be able to see the brick wall. How do two-way mirrors work? Light from the interrogation room hits the mirror and is made of glass that mostly reflects. So we have lots of light coming down from this light bulb, hitting the suspect, their face. Let's say there's 100 units of light, 100 photons that hit, and they bounce this way. So we have 100 units 100 photons of light bouncing off of his face onto the mirror. Most of it is going to reflect. Let's say we have 90 photons that bounce out, and that leaves 10 that go in. So the policeman can see a dimmer image, only 10 photons coming from his face. You still see it, just not as many photons, so it appears dimmer. The suspect is going to see their reflection. A tiny bit of the light of the suspect will refract and be seen by the police. Okay, that's one direction. This is a two-way mirror. Light goes in both directions. So let's look at this. In the observation room, they always have the lights much more dim. Let's say they only have 10 units, 10 photons coming down off that dim light bulb, hitting the policeman in the face and bouncing off. So we have 10 units going towards the mirror. Now, most of the light is going to bounce back. 9 units will bounce that way, but one of the units will go forward. And so in this situation here, some of the light from the policeman will end up going to the suspect, but it's only 1 photon. There are 90 photons from the suspect's reflection that are bounced back. So the 90 is going to overwhelm the 1 photon here, and the suspect really isn't going to be able to see that 1 photon very well. So the suspect's not going to be able to see the image of the policeman. And then the policeman over here has less light coming at him from his reflection compared to the light from the suspect. So the observer back here is going to see the light from this room overwhelming the light from the reflection. Now these numbers are pretty close. In real life, these numbers would be much different. So you'd be able to see a much more clear image over here compared to the reflection. So let's fill in the blanks. Number 6, the observer's room is kept very dim. The small bit of reflections and refractions coming from the policeman are covered up by the light from the suspect. The same can be seen in your home windows as you look out at night. When you're inside the house looking out your window at nighttime, there's very little light coming from the outside coming in. However, there's a lot of light reflecting off of the inside of the light, off the window from your face. And so as you look out the window, it looks more like a mirror. Okay, next line, next page. How do rear view mirrors work? Let me go and grab one of these rear view mirrors so you know exactly what I'm talking about. Not all cars have these anymore. Some of them have fancy electronic versions. And so if you have never seen one of these, I don't blame you. But we have a little flippy flap down here that turns it from a night setting to a day setting. In one of these settings, the images are nice and bright, and in another setting, it's dimmed. So you'd want to put it on the dim setting at nighttime so that when the bright headlights are shining behind you, the bright headlights are not as bright and they don't hurt your eyes as much. So exactly how does this work? And the answer is because it tilts a little bit. Here it's more vertical, and then we flip the flap and it tilts it this way a little bit. Okay, the night setting in a rear view mirror is designed so the headlights behind you are not too bright for your eyes. Look at the illustration below. A silvered material coats the back of the mirror. Draw a thick black line on the back of the mirror and label it silver backing. What do you think D and B stand for? Well, the D is going to stand for dim, and the B is going to stand for bright. So in this situation, we have the headlights coming from the back. This is the night setting. Bright headlights. And when it hits the front surface of the glass, some of it, only a little bit of it, will bounce off the front surface and bounce back to your eyes. Since it's just a little bit of light bouncing that way, it's going to be a dim setting. However, most of the light is going to go into it, it's going to refract into the glass, bounce off the silver backing, and most of the light is going to end up hitting the person's forehead. And so as you look at this kind of a driver, you would see the bright light up high. When we put it onto the daytime setting, what happens is that we tilt this mirror so that all the angles are a little bit more vertical, and this bright light ends up hitting your eyeballs, and the dim setting ends up hitting your nose and your mouth. So number 9, is the glass here made to have light mostly reflect or refract? Most of it goes into the glass, bounces off the back and comes out. So it mostly refracts. Number 10, we already mentioned, it angles the mirror at a different verticalness. How are rainbows made? Label 5 of the boxes in the diagram with the letters from the list. Not all the boxes will be used. You will choose the boxes that are best used. Okay, to do this, we should first look at this video right here. I will let you watch that on your own. Okay, so here we have the white light coming in. So that is letter A. Sunlight of all colors comes to the raindrop. Some of it is going to reflect off the drop, and looking at the angles here, here's the normal, theta incidence, theta reflection, so some of it's going to bounce up this way. That's letter B. Letter C, some of the light refracts into the drop. Different colors refract to different degrees and separate. So that happens right here at this surface here, C. You could also say that it's that area right there as we see the colors spreading out. Letter D, light reflects off the back of the drop. That's happening right here. Some light refracts out into the air. A little bit goes that way. But we're going to be mainly concerned about the reflection in here. Okay, light reflects off the back. Letter E, light again passes the surface, the drop, and the refracts as it enters the air. So that's right here, E. Different colors refract to different degrees, separating away from each other even more. And so now this person here sees blue to violet, blue, green, etc. So the main idea here is that to make a rainbow, you have to have the sun behind you, because we're seeing the reflection, and we have 3 processes. We have refracting at this point to separate the colors a little bit, and then it reflects off the back, and then it refracts again as it leaves. You need to know those 3 processes in order. How do fiber optic cables work? If we do our Snell's law and figure out the exact angle that the light rays leave the diamond and go into air, we'll see this kind of a pattern. Let's see here. This is air and this is diamond. And so this is faster. And the the light is slower in the diamond. Faster means that it's a bigger speed. And so it's going to make a bigger angle up here. If this is 10 degrees, this is going to be something bigger than 10. And as we go to the bigger and bigger angles of incidence, we're going to get bigger and bigger and bigger and bigger angles. In fact, at this angle right here, it's going to be virtually 90 degrees. The light that is angled this way is just going to skim the surface. If we try to do it with this angle here, 40 degrees, something strange is going to happen. It can't get any bigger than 90 degrees and still be in the air. And so what happens is that this surface now suddenly flips to be just like a mirror, and it's going to bounce off at 40 degrees. It's no longer going to obey Snell's law, it's going to obey the law of reflection. Number 13, if the angle of incidence in the slower medium is too big, total internal reflection is going to happen. And this occurs at a critical angle, which in this case is 33.38 degrees. When you have the incoming angle bigger than the critical angle, your calculator will say error. It won't know what to do. It can't do the Snell's law with an angle bigger than 90 degrees. It's just going to say syntax error or just simply error. And this happens in fiber optic cables. Let me move the screen up a little bit. Fiber optic cables are made out of special plastic that is very dense with light, just like diamond is. And so we can use that to change computer code and sounds into pulses of light like Morse code, flashing on and off. And one set of code will be sent down in one color of light, and it's going to bounce with total internal reflection. And then it'll bounce off that surface. And then it'll bounce this way. And it will keep on bouncing. It will not leave even if you bend the cable around corners. And so you can send light a very long distance, and of course, it's very, very fast. It's light. Light rays always hit the surface at angles greater than the critical angle due to the thinness of the fiber and the fiber's density. It's true even if fiber takes a turn around the corner. Thousands of conversations and web pages can be transmitted over each line, each with its own color. So when I have a conversation on the phone, then it might be sending that pulsing of Morse code with yellow light, and then somebody else can be talking on the exact same fiber optic cable with blue light, and another conversation with yellow light, and another one with yellowish blue light, etc., etc. And so you can have up to 340 signals down the same cable, the same fiber. And they don't just have one fiber strung up on the telephone pole. They might have hundreds of strands in one cable about that big around. And so you have hundreds times 340. So you could have from 30,000 to 300,000, somewhere in there, but thousands and thousands of conversations and computer codes going down the exact same cable that's up on the telephone poles. If you didn't quite understand something about this lesson, it is all written out for you at the back of your packet. And here is your homework. This is on Schoology, and I have changed the multiple choice to be fill in the blank. I have not explained in this lesson how to do numbers 4 and 5. And so at this moment you can skip those If you've not learned yet the equation for lenses, if you have learned that equation, then go ahead and do them. And that's the end.